Hassler here. I'm going to be doing notes with you for 6.9, integrating with U-Substitution. All right, so there are two ways or two approaches when it comes to this U-Substitution. First of all, this U-Substitution would be similar to me saying that we're going to do the reverse chain rule. So if you hear me say reverse chain rule, I'm talking about this U-Substitution. Reverse chain rule. And there's one simple way and there's a more difficult way. So let's talk about rule number 1. What happens if x is being multiplied by a constant k? Now remember, chain rule deals with a composite function. A composite function means that I have some function inside of another function. And so when I have the indefinite integral or definite integral, but we're just going to focus on indefinite integral of f of kx dx, notice that I have a kx, a linear function, inside of the f function. Now, when we do the chain rule, we take the derivative of the outside, whatever was inside stays there, and we multiply by the derivative of the inside. For antiderivatives, we are going to do something similar. We are going to do the antiderivative of the inside. Antiderivative of little f is capital F. Whatever was inside stays inside. Okay, so kx. And then instead of multiplying by the derivative of the inside, we are going to divide by the derivative of the inside. And dividing by the derivative of the inside is the same as multiplying by 1 over the derivative of the inside. And then don't forget, since these are indefinite integrals, I have a plus c. Okay, and so we're going to do a couple of examples and I'll talk to you about how to check it. But again, notice that in these examples, my inside function is a linear function. That means these are simple reverse chain rule integrals, okay? And so again, when I go to do these problems, I'm thinking to myself, hey, I'm really going to be integrating this 4x cubed dx. It's just that I have to deal with whatever was inside, okay? All right, so the antiderivative of 4x cubed, well, I'm going to add 1 to the exponent. I've got 4 divided by 4. It's going to become 1. It's just that instead of saying x to the 4th, we have to say, well, whatever was inside stays inside. So I really have 4 over 4 inside 2x minus 7 to the 4th plus c. And then my new rule says that I have to divide by the derivative of the inside. Dividing by 2 is the same as multiplying by half. So if I clean this up a little bit, my 4's divide out. I have 1/2 times the quantity 2x minus 7 to the 4th, and of course plus c. Now if I wanted to check this, I could take the derivative. And when I take the derivative of my answer, I should get what I was given, right? We said a derivative undoes the antiderivative. And so if I were to take the derivative with respect to x, that means I would say 4 times half is 2, x cubed, whatever was inside stays inside, times the derivative of the inside, and 2 times 2 is 4. I would get 4 times the quantity 2x minus 7 cubed, and the derivative of a constant is 0. So that's how I know that I took the correct derivative. All right, so I'm going to erase this so I have room. All right, but you can always check your answer to make sure that you found the indefinite integral correctly. Okay, let's do the next one. So my next one, I have the antiderivative of sine of 8t plus 3. What I'm really going to do is find the antiderivative of sine of t, and then I'm going to deal with whatever was inside. All right, the antiderivative of sine. Well, the derivative of cosine is negative sine, but there is no negative here. So really the antiderivative of sine would be negative cosine. Whatever was inside stays there. So of 8t plus 3. Okay, I got to divide by the derivative of the inside. Dividing by the derivative of the inside is the same as multiplying by 1 over the derivative of the inside. And then I have a plus c. So I really have negative 1 over 8 cosine of 8t plus 3 plus c. Again, you could take the derivative of this. when you take the derivative of the inside, which is 8, and you multiply that by 1 over 8, that's going to make the coefficient go away. All right, finally, in this particular problem down here, I've got an e function. And remember, with the exponentials, the inside function is always the exponent. And so what I'm really doing is I'm really taking the antiderivative of 12e to the x, and I'm going to deal with the inside function. Okay, so the antiderivative would be 12 e to the 7 minus 3x divided by the derivative of the inside, or times 1 over the derivative of the inside. And when I simplify this, 12 divided by negative 3 is negative 4, e to the 7 minus 3x. Oops, what did I forget? I forgot a plus c. Okay? All right, so again, if you notice, all of these are linear functions. All right, all of these inside functions, I should say, are linear functions. And so those are going to be the easy functions. What happens, though, whenever my inside function is not linear, right? In this example, under the rule number 2, I have a cubic function inside. So that's going to make things a little bit more difficult, or a lot more difficult, okay? So again, U-substitution is like the reverse chain rule, which means that I'm dealing with a composite function. And when we deal with a composite function, we're always dealing with this inside function and this outside function. And what I want to do is I want to identify the inside function, and I'm going to call that inside function u. Okay. Don't know what's happening with my pen, sorry. All right, and so that's going to be my goal, is to identify the inside function and set it equal to u. Well, my inside function is x cubed plus 4. I'm going to say u is equal to x cubed plus 4. Now, the reason why I would do this is because I want to integrate a much simpler function, right? So I'm going to rewrite this. I've got the antiderivative of 3x squared, but now instead of x cubed plus 4, I'm going to say u to the 5th. All right, and we're going to hold off on this dx for a second. All right, so again, my job is to make the function much simpler to work with. And if I'm going to have to integrate u to the 5th, I would rather integrate u to the 5th than integrate x cubed plus 4 to the 5th. Oh yeah, and there's 3x squared, right? So I'm going to transition everything over to u's. Okay, so rewrite using u, or in terms of u. Now remember, over here for rule number 1, we said that we were dividing by the derivative of the inside. Okay, so that means I want to find the derivative of the inside. I'm going to find the derivative of u with respect to x, and that's going to be 3x squared. And I want to replace this dx. Like, I want to get this expression, set equal to dx so that I can replace the dx. All right, so I'm going to multiply both sides by dx. It means du equals 3x squared dx. I'm going to divide both sides by 3x squared. So I get du over 3x squared equals dx. And so I'm going to replace the dx in my integral, this right here, with du divided by 3x squared. And I am happy about doing this. And I'm happy about doing this because what I notice is that this 3x squared and this 3x squared are going to undo each other. Remember over here in rule number 1, we divided by the derivative of the inside. That's what I'm doing. I'm dividing by the derivative of the inside. And what happens is when I divide by the derivative of the inside, it's going to divide out with the extra function that's in this definite integral. And now what I really have, I'm going to erase these plus c's over here so I have room. Now what I really have is the integral of u to the 5th du. And that is so much easier to integrate than that messy function that was given to me in the first place. So let's integrate, okay? I've got u to the 5th. So I'm going to add 1 and divide by my new exponent. So I have 1/6 u to the 6th plus c. And then I'm going to go ahead, and what I'm going to do is I'm going to take what u was equal to, and I'm going to replace u here. with what it was equal to. So I really have 1/6 in parentheses x cubed plus 4 to the 6th, and then plus c. And again, I could always take the derivative to double check. If I take the derivative, so if I take the derivative of this function with respect to x, right? 6 times 1/6 would be 1. So I would have x cubed plus 4 to the 5th times the derivative of the inside, which is 3x squared. That matches what was given to me. So this is my final correct answer. So again, this magic that happens, just like in rule number 1, just a little, elevated in rule number 2, is I'm still dividing by the derivative of the inside. And in dividing by the derivative of the inside, I am dividing out this extra function that's up here. So I have a couple more down here that I'm going to do with you, and then I'm going to give you a chance to try some on your own. And so if you take a look at this very first problem has a linear function to it. And so this is going to be very similar to rule number 1. So I'm going to let you try that one on your own. But if you take a look at example number 2 is an e function, not a linear function inside. So I'm going to do this one with you. Okay. And so my inside function, my u function, is the cosine function. And I'm going to take the derivative of that inside function. So du d theta. The derivative of cosine is negative sine. And then I'm going to get the d theta by itself. Okay, so I'm going to multiply both sides by d theta, so negative sine of theta d theta. I'm going to divide both sides by negative sine of theta. So du divided by negative sine of theta equals d theta. Some of you guys are going to get really quick at doing this, and you're just going to be able to see it, and you're not going to have to write everything out, okay? And that would be the goal. The goal would be to be able to just see what is happening and not have to write anything out, but we're not there yet. Okay, so what I'm really doing is I'm really integrating sine of theta e to the u, and then I'm going to replace d theta with du over negative sine of theta. Okay, that was the goal. The goal was to find what d theta would be equal to so that I could replace d theta with du sine of theta. And this is really good news because, as I mentioned up above, the derivative of the inside is going to divide out with this extra function. That should always happen. Now, in this case, I have a little extra something left. I have this negative left. So what I'm really doing is integrating negative e to the u du. And the really good news for me is that the antiderivative of negative e to the u is just negative e to the u plus c. And then I got to go back and I've got to replace that u with what u is equal to. So my final answer is negative e to the cosine of theta plus c. That would be my final answer. Okay. Okay, I'm going to go ahead and do number 3, and then I'm going to press pause, and I'll have you guys press pause so that you can try the other ones and then check your answers. All right, so let's take a look at 3. Again, I'm identifying the inside function, and I'm going to call that u. So my inside function is square root of x minus 1. And I got to take the derivative of this inside function, so du with respect to x. Now remember, x is really, square root of x is really x to the 1/2. And so the derivative of x to the 1/2, we should be fairly familiar with at this point, right, is 1 over 2 x to the negative, 1/2 x to the negative half, rewritten as 1 over 2 square root of x. All right, my job is to get set equal to dx, right? So it's just like this quick flip-flop, right? I would multiply both sides by dx, and then that's going to put dx on top. And then I'm going to multiply both sides by, in this case, multiply both sides by the 2 square root of x. And so I really have 2 square root of x du is equal to dx. Okay, and now I'm ready to start rewriting my integral here. Okay. So let's see, I've got the antiderivative of u squared over the square root of x, and I'm replacing dx with, so times 2 square root of x du. And again, if you take a look, this is magic every time. The derivative of the inside divides out with this extra function. And so what I'm really doing is I'm really taking the antiderivative of 2u squared du, which is way easier to take the antiderivative of than that messy fraction square root thing that I was given. And so the antiderivative would be, let's see, 2 comes along for the ride, add 1 to the exponent, and divide by that new exponent, plus c. And then I can go back and I can replace the u. So I really have 2/3 square root of x minus 1 on the inside cubed, and then plus c would be my final answer. All right, so what I'm going to do is I'm going to press pause. I want you to press pause. I'm going to write the answers out for 1, 4, 5, and 6. When you have an answer for 1, 4, 5, and 6, go ahead and hit play, and you can check your answers. I'm not going to show the work for them in the video, but you can go check my answer key that's posted, and that has all the worked out solutions for you. Let me know if you have questions. Okay, so let's go ahead and take a look. Answers that you should have for problem 1, that was just a linear function inside. And so antiderivative of x to the 4th would be 1/5, x to the 5th. Whatever was inside stays there, times 1 over the derivative of the inside, or dividing by the derivative of the inside. 4, 5, and 6 were leveled up, right? Those were not linear functions on the inside. So I went ahead and wrote out for you what the inside function was, and then what dx was isolated. And so you would go ahead and do that replacement. Your final answer for 4 is 2 square root of tangent of x plus c. 5 is 1/8, quantity of t squared plus 9 to the 4th plus c. And 6 is 1/12 times the natural log of x to the 6th plus c. Again, if you need to see those worked out, you can go check out my answer key. Your job is to work through the task card practice, complete your work on a separate sheet of paper as evidence, and I will get answers posted for you. Please email me whatever questions you have.